Hey, fellow mathers. Before we get into this episode, we want to share with you how you can get access to free content, professional learning that will keep your students engaged and doing the math that matters. Get ready to go to this link, mathisfigureoutable.com/challenge.
That's right. Registration is open for the free Math is Figureoutable Challenge that's starting May 15th and runs to the 17th at 7 p.m. Central. We're going to have 3 nights jam-packed with learning and routines that you can take straight to your classroom.
In these challenges, we have a great time. We do some math, talk about classroom experiences, give away super cool bonuses and prizes. You won't just walk away with routines that are naturally engaging and encourage your students to think mathematically. You'll also have a chance to win over $6K worth in prizes, including a few virtual PD sessions for your school. I'll be joined by my wonderful co-host Kim and special guest Jenna Labe.
You can register at mathisfigureoutable.com/challenge for a fantastic learning experience. That's mathisfigureoutable.com/challenge. Now on to the show.
Hey, fellow mathematicians, welcome to the podcast where math is figureoutable. I'm Pam.
And I'm Kim.
And we make the case that mathematizing is not about mimicking steps or memorizing facts, but it's about thinking and reasoning, about creating and using mental relationships. Y'all, we take the strong stance that not only are algorithms not particularly helpful in teaching, but that mimicking algorithms actually keeps students from being the mathematicians they can be. We answer the question, if not algorithms and step-by-step procedures, then what?
So last week, we revisited the development of mathematical reasoning, which we had...
in a little bit of a less precise way. I misspoke several times. Kim saved me. Anyway, sorry, Kim, keep going.
It's all good. So we tackled that a little bit in episodes 5 and 6, and we decided to have a revisit. And so you got to add on a couple of things that you felt like were really important to share. And we did a couple of examples of counting and additive thinking for some different problems.
And we talked a lot about how we could be solving an addition problem, but if students are actually using counting to solve it, then even though they're solving an addition problem, they're thinking in the level, they're using reasoning in the level before, in the less sophisticated level. And we don't want that. Like we have to accept where kids are, but then we want to move them on. We want to help them develop as more and more sophisticated reasoners using additive reasoning. So like you said, we gave some examples of how we could give an addition problem or a subtraction problem. Both of those live in additive reasoning, or should, and how kids might solve them using additive reasoning, or they might be solving them using less sophisticated counting strategies, and how we can sort of differentiate between those two. Well, today I want to talk about an outcome of that. So often in our education system, we say to kids, here are some problems, solve these problems, and we give them single digit addition and subtraction problems, lower number addition and subtraction. And then once kids get answers, we kind of move on. We say, all right, now you've got that. We're going to teach you how to add and subtract bigger numbers. And all too often in our education system, when we do that, okay, it's about bigger numbers, then we sort of force a step-by-step procedure. We force an algorithm and we say, okay, here's what addition of bigger numbers means. And that's a fallacy. It's not what it means. It's a way to find answers using a step-by-step procedure that could solve any problem in the class. We call those algorithms. They are step-by-step procedures that I could give you any numbers and you could follow those procedures to find the answers. Computers need those algorithms. Humans do not, but all too often in our education system, we say, all right, line those numbers up. And so if I give you a random problem like 36 plus 99, y'all, if you're listening to the podcast, you might just scribble that number down. Just scribble the problem 36 plus 99 down. And line them up like we traditionally do when we give kids those bigger number addition problems. And then we typically in American or in lots of education, we typically say to kids, okay, you're supposed to add 36 and 99, but now don't think about 36 and 99 anymore. Now I want you to focus just on the digits, just on the ones. I just want you to focus on the 6 and the 9. And in that first step of the algorithm, we actually work against kids' intuition. We work against average intuition because kids are at that point thinking about 36 and 99. They're grappling with what those numbers mean. They've counted to those numbers probably at this point, but they don't really have a vast network of connections about them. They're starting to think about 36 as 30 and 6, maybe as 4 away from 40. They might be thinking about like it's not 20 but it's 30, and then it's sort of in between 30 and 40, a little bit further than 35. Like they're developing kind of a network of connections about what 36 means. Similarly for 99, they might be thinking about 90 and 9, or ooh, it's almost 99, 100, it's almost 100. They might be thinking about those in that algorithm, step-by-step procedure. When we say, okay, don't think about the big numbers anymore, just focus on the 6 and the 9, you could conceivably have a kid go, whoa, that feels weird. I'm thinking about 30 and 90, not 6 and 9. Okay. Wow. I guess I'm not a math person, because I'm not, it's not my intuition. It's not my gut instinct to think about those small numbers. That's weird. Okay. All right. I'll do what my teacher tells me to do. I guess I'm not a math person. I guess in this moment, I'm proving to myself I'm not a math person, because that wasn't my first inclination. Darn. Okay. All right. I'll do what my teacher says. Y'all, we want to avoid those moments at all costs. The moments where we say to kids inadvertently, and nobody, of course, is doing it intentionally, but those moments where unintentionally we say to kids, you're not a math person. Just do what I say. Don't
Right.
do what your natural
Right.
inclination is. So let's keep going. We want to avoid those moments, but notice if I'm doing the algorithm, I'm stuck there in that moment. Now, could you agree with me that a kid could say, I'm supposed to add 6 plus 9? That's what my teacher just told me to do. That's the first step, 6 plus 9. Could a kid go 6, 7, 8, 9, 10, 11, 12, and count all the way up to 15 and put down the 5 and carry the 1 over into the next column? Could you agree with me that they are now looking like they're an additive reasoner, but notice that that kid was just counting? Now, that kid to add 6 plus 9 might have thought about 9, 10, 11, 12, 13, 14, 15. They might have started with a bigger number. Okay, we prefer that. That's a better counting strategy. Better meaning it's more sophisticated. I'm thinking about adding on or counting on from the larger. That's great. But I'm still using a counting strategy. If I'm following that step-by-step procedure, now I'm over in the tens column, then I might think about, okay, now I have a 1, a 3, and a 9. I've got to add those together. It's so important. How does that kid now add that carried 1, that carried from over, that regrouped 1, which really represents a 10? Now, as they're thinking about that 1, 3, and 9, how do they do that? Could you agree with me that a kid could conceivably count again? They could be like, okay, 9, 10, 11, 12. Like they could add those together. They could, count those one by one, get that correct answer, write it down. And now we think, oh, good. Now that you've written that down, you've got those two numbers. If I add, by the way, that's 13. So if I add those together, now I've got 1, 3 next to that 5 I wrote down earlier. And so I'm saying to myself, okay, that's 135. And the kid writes that down, and we're like, yay, you're an additive reasoner, because they got the answer to an addition problem correct. So we like, yay, you're an additive reasoner. When in reality, that kid was thinking using counting strategies the whole time.
Mm-hmm.
And if we were doing this live right now, I would draw a frowny face on the board. Because too often we focus on the fact that the kid got that answer correct. Right. So we're like, good job, you're thinking additively, because they got an addition answer correct. But how were they doing it? If they were doing the algorithm, they may have been using counting strategies, not sophisticated enough. And what we would suggest, Kim, is that in this moment, if a kid is using those counting strategies, we need to do some more work with smaller numbers to get that kid thinking additively with smaller numbers before we maybe move on to try to get them to think additively with bigger numbers. Now, you might be thinking, Pam, Kim, my kids are doing the algorithm, but when they do it, they're not using counting by 1 strategies. They're using additive reasoning. So again, back to our 36 plus 99, they might be looking at that 6 plus 9. My kids, Pam, my kids are thinking about 6 plus 9 as, let's see, I could do 6 plus 10. That's 16. I'll just back up 1 to get 15. Or they might be thinking about, I could think about 6 plus 9 as 9 plus 6. And I can go from 9 to 10. I can get to that friendly 10. 9 to 10 is 1. I've got 5 left over. 10 and 5 is 15. Pam, they're thinking additively while they're doing the algorithm. Okay. I could agree with you. I could submit that you could be correct that your kids are thinking additively as they're doing the traditional algorithms. However, how big of numbers will that student ever think about additively if they are doing the traditional algorithm? They'll think about the algorithm, even if I have a long number, lots of digits, added to another long number, lots of digits. Every time I'm thinking about columns of digits, columns of single digits. The biggest I'll ever be able to think additively about those numbers is with those single digits.
Right.
And what we're suggesting is that's not big enough. It's not sophisticated enough. It's not enough work in getting kids thinking additively about those big numbers. Now, somebody's probably thinking, but Pam, you can't think additively about numbers like 36 and 99. You have to line those up. Like you have to line those up and then add the columns because you can't think additively about 36 and 99. Or can you? Now, if you've listened to the podcast at all, you've heard us do this problem or one like it lots because we wanted to sort of exemplify additive reasoning. But Kim, I'm just going to ask you, how would you add 36 and 99? What's one additive way of adding 36 plus 99?
36 plus 99. I would add 36 plus 100, which would be 136, but I added one too much. So then I'm going to remove one at the end to get 195.
100 and...
I'm sorry, 135.
Sweet! It's catchy! I'm not the only one that misspeaks. That's
135.
Hilarious. Okay, so Kim is an over strategy girl, and I had a feeling that that's what she was going to do, so I'm glad I asked her. So she's like, I'm going to add 36 plus too much, and then back up. Totally cool. Could you also do a little give and take? If I've got 36 plus 99, I could think about, 99 is almost 100, so I could add just 100 plus what's left over, 35. 135 is 135, Kim, not 195. Okay, cool. So those would be some additive ways of thinking about bigger numbers. And we need students to think about bigger numbers additively, not using counting strategies. All right. So we thought we'd spend some time on this podcast thinking or exemplifying how that can happen with multiplication as well. If multiplicative reasoning is more advanced, more sophisticated, I'm grappling with more and more things simultaneously, multiplicative reasoning, than I am in additive reasoning. How do we build that multiplicative reasoning? What does it look like to solve a multiplication problem using multiplicative reasoning? And what does it look like to solve a multiplication problem using less sophisticated additive reasoning or less sophisticated counting strategies? Is that even a thing? So here's an example. Multiplication problem. Let's say I'm baking cupcakes and I know that I want to give 3 cupcakes for the 4 people I'm baking cupcakes for. I've got 4 people. Each of them need 3 cupcakes. How many cupcakes do we need? Could you picture a kindergarten kid solving that problem? Kim, what might we see a kindergarten kid do to solve that problem?
So a kindergartner might say, okay, I have 4 people. So they might draw 4 circles or 4 people even, and they might deal 1, 2, 3 to the first person, 1, 2, 3 to the second person, 1, 2, 3 for the third person, 1, 2, 3 for the fourth person, right? And then go back and count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and end with 12 cupcakes.
Bam! They just solved a multiplication problem. They must be reasoning multiplicatively. Or were they just using counting strategies to solve that problem? So young students can solve multiplication problems using counting strategies. That's great for a kindergartner. Right. When we get to 3rd grade and 4th grade, we need to start nudging them to, 3rd grade, we need to start nudging them to multiplicative or additive reasoning for sure, like repeated addition, and then multiplicative reasoning. I may have just given away what I wanted to do next, just a little bit. Kim, what would it look like for a student to solve that problem? You just exemplified counting. What if they were using additive reasoning to solve that cupcake problem?
So additive reasoning is going to look like skip counting. And so they might say 3 for the first person and then 6, 9, 12. 3, 6, 9, 12.
Yeah, they're sort of adding 3 every time. And they're able to do that using additive reasoning. And they've solved a multiplication problem additively.
Right.
That's super for a kindergarten and 1st grade kid.
Right.
Woo! I'd even be okay with that, a second grade student. Though I'd kind of maybe help them. I would hope some of them were thinking about 3, 6. That's 2 people. I could double that to get 4 people. Those are some sort of interim strategies that are kind
Mhm.
of half additive, half multiplicative. But by the time we get to where we want kids to be thinking multiplicatively, we need kids thinking multiplicatively about those 3 cupcakes for 4 people. What would that look like?
So if they don't know 3 times 4 is 12, a multiplicative thinker might think of, I know 3 threes is 9 and another 3 is 12. They might
Bam.
think about 2 threes is 6, double that to get 4 threes is 12.
If they happen to know something crazy like no, that's not a good example. Let's
Oh,
try a
if they
good one.
happen to know 5 threes is 15, then 4 threes would be 12.
Cool. So depending on what they know, if they can
Right.
sort of reason from there, then we would hope that that would be an example of multiplicative reasoning. So let's think about division because division lives in multiplicative reasoning. Can we have a division problem that kids could solve at all of the different levels? Again, with our emphasis on let them start where they are, but then we want to help them progress to think more and more sophisticatedly. So let's say random division problem. What if I said 36 divided by 9?
Why
36.
don't you give us a counting strategy for this
Okay,
one?
okay, I'll do this one. 36 divided by 9. We actually interviewed a student not too long ago with 36 divided by 9, and the student
Yes.
drew 9 circles on her paper. And she said,
Mhm.
okay, we got 9 circles, and I need to divvy out and deal out 36. And so in each of the circles, she drew like 1 tick mark. So 1, and then she like 1 in each of the 9 circles, 2 in each of the 9. Like she's literally drawing tally marks. So now each circle has 2 tally marks. And as she's doing that, she's counting. So I've got 9, and then 10, 11, 12, and she did it all. Now I've got 18, and then she keeps dealing out. Now I've got 27, and then she keeps dealing out, and now I've got 36. And then she said, okay, I've dealt out all 36 because she counted each of those tally marks. I've dealt out all 36. Then she looked back at each of the circles, and each of the circles had 4 tally marks in
Mhm.
it. And
Mhm.
almost as if it's a surprise at that point, she's like, ha,
Yeah.
4, 4,
Yep.
4. 36 divided by 9 is 4. Woo, who knew?
Yep.
That would be a counting strategy
Right.
for a division, a multiplicative problem by nature, but using a counting by 1 strategy. We've also seen kids where they're bigger numbers when they've done that, but they don't actually, when they see the 4 in there, they actually then have to count. Oh, and she didn't have to count the 4 because she could just recognize she sabotaged those 4. But if a quotient is a bigger number, then they might have to actually count what's left in that circle
Right.
even one more time where they're
Right.
sort of counting. Okay,
Right.
so 36 divided by 9, Kim, what would be an additive strategy for 36 divided by 9?
So additive, they might be thinking about 36 subtract 9
Mm-hmm.
to get 27, subtract 9 to get 18. Or maybe skip counting 9. If they skip count by 9s, well, they might say 9, 18, 27, 36, and then the number of counts would be their quotient.
Mm-hmm. So either the number of subtractions or
Mhm.
the number of sort of
Mhm.
skip count up, those would be additive reasoning ways of solving
Right.
that division problem.
Mhm.
Yeah, totally cool. Okay, so then what would a multiplicative reason? Like how do we hope kids think about 36 divided by 9? Okay, I want to go first.
Okay.
So y'all, we hope students for both the multiplication and the division problem. So I don't know if you heard when I asked Kim the 3 times 4 cupcake problem, the very first thing she said is, well, if a student doesn't just know 4 times 3, then we would hope they would think multiplicatively this way. Well, I would say the similar thing for division.
Right.
If a student doesn't just know 36 divided by 9 is 4, or doesn't just know, well, let's say I'm dealing with 9s. What do I know about 9s? Oh, well, I know 9 times 4 is 36. Therefore, 36 divided by 9 is 4.
Right.
We would kind of hope that eventually we get there. That's like our ideal. But we can also reason if we don't know that. And we need this reasoning for all of the myriad facts that we don't just know. So of course we hope kids know 36 divided by 9. But boy, there's a lot of division problems that no one's going to just know, that we need
Sure.
them to be able to think similarly about. So what would be a multiplicative reasoning way? I did one, Kim. You have to do
Okay.
another.
So I know that a lot of kids can think about 18 divided by 2, or 18
18 divided
divided
by
by
9.
9, sorry,
Hmm.
is 2. 18 divided by 9 is 2. So knowing that, they can also think about that twice. So 18 divided by 9 twice would be 36 divided by 9. So their answer would be 4.
So kind of like if I'm thinking about, I know that 9 times 2 is 18. And
Mhm.
if I know that and I double the 18 to get 36, then
Mhm.
it's going to have to be 9 times 4 is 36. And I can use that reasoning about multiplication to think about division. You kind of said it in a more division way, which is totally cool. But I could also think about it in a more multiplicative way or multiplication way, to find that division problem.
So this is helpful to parse out the difference between counting, additive, multiplicative thinking. But
Hmm.
but I also don't want to leave today without a little bit of application. So how can teachers help their students if they're stuck in counting or additive and they want them to be in multiplicative thinking?
Yeah, absolutely. Let's talk about that because our big upshot is, how do we help students progress?
Right.
Like, let's acknowledge where they are. It is a necessary starting point. We need kids to solve the problems the way they naturally do it. But then we can't rest on our laurels. We can't stay there. We have to help them progress. So, in a little bit of time that we have to finish out, let's mention a few things. So, what we are not suggesting is traditional review.
Right.
Traditional review where we say to kids, you should have learned this already, and so we're
Oh,
going to go, and
yes.
we do the same thing that has been done before. Go memorize your multiplication tables, like whatever it is that hasn't worked in the past. If we try to redo that, it doesn't work. Like, redoing stuff that didn't work in the past is not now going to magically work this
Right.
time.
Right.
So we're not recommending traditional review. We do recommend that we acknowledge where they are. We know our kids. That's the of our mantra: know your content, know your kids. You got to know your kids. So you got to figure out where they are in the landscape. And then know your content means, how do we then expose them and help them construct the more sophisticated things? Well, that's why we love problem strings, because problem strings are all about multiple access problems, problems that give all kids multiply. They give all kids access. So no matter where the kids are, we give them access to the problem. They can solve it using what they know. But then in the share, we expose them to more sophisticated strategies. We help them connect what they were doing to something that's more sophisticated, that's higher in that level of reasoning, that is using something more and more simultaneous. So we give them a problem, students solve it however they can. Then we ask certain strategies to be shared, and we say, how were you thinking about that? We help connect less sophisticated strategies to more sophisticated strategies. And then, so important, next problem. And the next problem is a chance for that student to then say, ooh, how can I use what I just was exposed to? How can I use that on this next problem? And that is the process of construction, where they get a chance to go, I'm going to grapple with these relationships using what I just sort of experienced, using these things that are pinging in my head from the problem before. I'm going to now attempt to do that in the next problem. And then beautifully, we share strategies, and students can, oh yeah, that's how I could have, even if they weren't successful in that next problem, but they were grappling with it. They now get a chance to go, oh, like that. Oh, and then the teacher expertly helps connect strategies, and then brilliantly, the next problem. So you might have heard, oh, so let's go do problem talks. Let's just go do number talks, because then they'll see what everybody else is doing. It's not enough to just see and experience once what someone else is doing.
Right.
We need that next purposely planned problem for the chance to grapple with trying it. And then we need that next purposely planned problem with the chance to grapple with trying it. Then we need that next purposely planned problem. Now by maybe we're grappling well with it, we're using it well. Now we get a chance to, wait, that next purposely planned problem gives us a different way of applying it. Or maybe it's a pushback problem where that strategy doesn't work so well. Like problem strings are designed on purpose to give us those opportunities to construct those relationships in kids' heads. That is a huge way, can be your go-to strategy, teachers, to help students progress from where they are to that next more sophisticated thinking.
Absolutely. So, Pam, one more thing before we go. We got the chance to interview a lot of students recently, right? Lots
Oh,
of kids
so
to
brilliant.
do this special project. Tell us about that a little bit.
I'm so glad that the REL Southeast, the Regional Education Laboratory Southeast at Florida State University, asked us to do a project where we created some professional learning around the development of mathematical reasoning. And then we created these infographics. We created one-page infographics to really exemplify and make it visual each of these levels of or these domains of reasoning. And they've just come out. We're so excited. They're totally free. You can absolutely download them. And the most exciting part of all of it that we have this graphical. We're making the thinking visible, but also we put in these videos of
Yeah.
real students solving real problems where you can see exemplified kind of what we just tried to do in this podcast and the last episode, where you actually get to see a student solving a multiplication problem using counting strategies, using additive reasoning, or using multiplicative reasoning. You get to see it in action as we interviewed all these students, and then we studied how they solved particular problems. And then we sort of sorted them out, and we gave you this really experiential way of learning more and more about these different levels of reasonings. Now, in the last episode and in this episode, we only got to counting strategies, additive reasoning, and multiplicative reasoning. Y'all, we exemplify proportional reasoning. You could see real students solving proportional reasoning problems using proportional reasoning, or maybe using multiplicative reasoning, or maybe using additive reasoning. Same with functional reasoning. Secondary teachers, if you're like, Pam, explain better, like more, I need to see functional reasoning in action. Bam, we've got it for you. Check out these wonderful resources. I'm so glad, again, that they asked us to create them. Kim, tell us about where they can get them.
Oh, yeah. So you can check out the blog at mathisfigureoutable.com and click on Learn Now, and you'll find the blog. And then if you want the direct link, you can just check out the show notes here.
Yeah, absolutely. So download those infographics. You can watch the videos of those kids. You're going to love learning more and more about developing mathematical reasoning. So if you want to learn more mathematics and refine your math teaching so that you and students are mathematizing more and more, then join the Math is Figureoutable movement and help us spread the word that math is figureoutable. Thank you for listening and making math more figureoutable.
To learn even more, make sure you register for our free challenge at mathisfigureoutable.com/challenge. You are not going to want to miss the evenings of May 15th through 17th, starting at 7 p.m. Central.
Math teaching, go register now. That's mathisfigureoutable.com/challenge. Join us to make math more and more figureoutable. And if you can't join live, register and we'll send you access to the recordings. We'll see you there.